This lesson is about symmetrical components, which is a technique used to analyze faults when the power system becomes unbalanced with the presence of the faults. So there are a few different types of faults which can exist in power systems. Some of them are symmetrical and some of them are unsymmetrical in nature. An example of a fault which is unsymmetrical in nature is a line to ground fault, and other examples are line to line fault or line to ground fault. And the example of a symmetrical fault is a three-phase fault or three-phase to ground fault. So when we have fault conditions, then the power system becomes unbalanced, and it requires that the fault current needs to be calculated in order to put the appropriate power system protection equipments on the power system. So the calculation of the fault current can be divided into two main types. One is faults short-circuiting all three phases when the network remains balanced electrically. So for these calculations, normal single-phase equivalent circuits may be used as we use in ordinary load flow calculations. Another situation is where you have faults other than the three-phase short-circuit fault. So for example, you have single line to ground fault. When the network is electrically unbalanced, so to facilitate those calculations, a special method for dealing with unbalanced networks is used that's known as the method of symmetrical components. So that's what this total lesson is based on. So here is the graph which is showing a balanced three-phase system. So in a balanced three-phase system form, here it's shown in the time domain form. So time domain form. And you can see how, let's say, you can take any phase. For example, let me take this as VA. And let's say this is VB and this is VC. Okay. So you can see that all of them has the same amplitude. When you measure it from 0, and where is the 0? This is where the 0 is, right? They have the same, all three has the exact same amplitude, right? And now the phase angle. So you can see that A has a phase angle of 0 degrees. B, so each square is 10 degrees. So this is 120. So B is lagging behind A by 120. That is how we can say it has an angle of negative 120 once we're gonna draw it on the phasor diagram, right? Now, with respect to C, so where's the 0 crossing for the C? Where does it start from? Here. Here you can see that it is 240 degrees. Okay, so you're aware that you can write it as, so you can write it as lagging behind by 240, and you're also clear that that's the same thing as a positive 120, right? So how do you see it? Any phasor which is placed, let's say this is VC, which is placed at so that's negative 240, and that's exactly same as positive 120 degrees. So you can write either one of them. So that's a balanced three-phase. You're gonna have the three phases, the voltage or the current, it does not matter, has the same amplitude. So for example, you can see on this phasor diagram or vector diagram that the amplitude of these three phasors, the length of these phasors, the length of the arrows is same. In other words, when you express them in their polar form, so here is the amplitude of the voltage for phase A, phase B, and phase C, which is same for all the three phases, which is V volts. And the other thing which you see when you see that the system is a three-phase balanced system, that's the phase displacement. So one was the same amplitude, second is the phase displacement. So the phase displacement of equal amount, and that equal amount is 120 degrees. So you can see that this has to be 120 degrees, this has to be 120 degrees, this has to be 120 degrees. Okay, so as you can see, A is at 0 degrees, B is at negative 120 degrees, and C is at positive 120 degrees. So this is a balanced system. Another way you can see is here, this is also 120 degree phase displacement between the three phasors, equal 120. Okay, so same amplitude again, the same length of the phasors, but what else you see is, you can see A has an angle of 0, C has an angle of negative 120, and B has an angle of positive 120, right? Because again, when you go counterclockwise, you measure the angle positive. When you go clockwise, you measure the angle negative. Positive. Okay, so this whole graph is a balanced three-phase system. Now this is shown in the okay. Now what happens in case of an unbalanced system? Although we understand that what are the causes of the unbalanced state, and we saw that the cause of the unbalanced state is the fault. But let's try to understand what happens when a system is unbalanced. So neither the angular nor the amplitude relationships exist. And if either one of them is not there, it is unbalanced system. Let's say if you have, let's say, VA, you have VAV 0 degrees, VB V 90 degrees, VCV 120 degrees. So this is, here you can see that they have the same amplitude, but this is still an unbalanced system. But in the example, what do we have? We have VA. First of all, the amplitude of VA is considered as double in comparison to the red and the green arrows. So if we consider the length of the red and the green arrow as V, the length of this arrow is, the black arrow is twice as V. Okay, so that means for VA, the amplitude is 2V, and it is as 0 degrees, so angle is 0 degrees. What is VB? So VB has an amplitude of V, and it is an angle of, and so clockwise, minus 90 degrees, right? That's fine. So C, you can see its amplitude is V, and in terms of angle, it is at positive 120 degrees. So you can see that the A, B, and the C do not have the same amplitude. At the same time, they do not have the angle displacement of 120 degree from each other either. So that's why this is an example of an unbalanced system. Again, the cause could be a fault. Okay, so unbalanced power system. As I said, unbalances in the power system may be due to the unbalanced sources, unbalanced transmission lines, unbalanced loads, or faults in the transmission system. Now, for analyzing an unbalanced power system, we use symmetrical components method. So how that symmetrical components method work? An unbalanced system can be represented by a set of, so not only one, a set of balanced systems. So first step for analyzing the unbalanced systems using symmetrical components is the unbalanced system will be represented by a set of balanced systems. Number 2 will be analyze each member of the set. So whatever set of the balanced systems we have, then you complete the analysis for that. The third is use the principle of superposition to combine the results of all the sets into one. Okay, so that's an explanation how we're gonna handle or how we're gonna approach using this method of symmetrical components. So, solution to unbalanced systems, symmetrical components. It's a powerful technique for analyzing the unbalanced three-phase systems. And what we do is linear transformation from phase components to a new set of components called symmetrical components. Any set of unbalanced three-phase voltages can be represented by three sets of three-phase voltages or currents that are called symmetrical components of the unbalanced set. So one three-phase voltage or current can be represented by three sets of balanced three-phase voltage. One set of unbalanced three-phase voltage can be represented by three sets of balanced three-phase voltages, and the same thing is true for current. And those are called the symmetrical components of the unbalanced set. A set of three-phase voltages, let's say, is given as VA, VB, and VC. These phase voltages are resolved into following three sets of sequence components. Okay, so we're going to say, so this is a one, let's say, write it like this, one three-phase system, right guys? One three-phase system. A, B, and C are the three phases of the same system. So one three-phase system is resolved into following three sets of sequence components. One is called zero sequence component. Second is called positive sequence component. Third is called negative sequence component. Now the zero sequence component, so the three sets are zero sequence component, positive sequence component, and negative sequence component. In a zero sequence component, what do we have? That set consists of three phasors. That has the same amplitude. The three phasors have the same amplitude, and they are at the same phase angle. So zero phase displacement with respect to each other. Okay, another set will be the positive sequence components. In case of positive sequence components, again, it has three phasors with equal amplitudes, but there is a 120-degree phase displacement of the positive sequence type, meaning they're going to be A, B, and C. So that means if you hold the phasor diagram in the center and you rotate and you're right in front of it and you rotate it counterclockwise, you're going to have B following A and C following B. So A is followed by B, B is followed by C. That is the ABC phase sequence, or in general we call it positive phase sequence as well. Okay. The third set of sequence components is called the negative sequence component. Again, it consists of three phasors, again with the equal amplitudes, again with a phase displacement of 120 degrees, but now it has the negative sequence. So that means it will be more like A, C, B. Okay, so in this case, again, if you have the phasor diagram of the three phasors in negative sequence, you're going to have A followed by C and C followed by B when you rotate it in counterclockwise direction. So that is how we're going to divide one three-phase system into three sets of sequence components. Okay, so here those are. So we have zero sequence, C. Is it following what we said before? Let's see. So you can see that they have the same amplitudes, same length phasors, same magnitudes, and they are at the same angle. So whatever angle with respect to the zero is, if you consider this as zero, like the 0 degrees, they all may be at an angle of 45 as an example, but they all are at 45. So with respect to each other, the phase displacement is 0. They are in phase. Okay. Then is the positive sequence. Positive sequence. Now in positive sequence, so same amplitude, same phasor length, same amplitude, and the angle displacement is 120. So this angle displacement is 120. And then you have, so you're going to hold it in the center in here, and you're going to rotate it counterclockwise direction. Once you see it rotating, you're standing right in front of it. You're going to see B is following A and C is following B, or A is followed by B, B is followed by C. So A is followed by B, B is followed by C. Okay? And you can start from anywhere. So for example, you can start from B. So B is followed by C, C is followed by A. Okay? Or you can start at C as well. C is followed by A is followed by B. Positive sequence. And how they are represented, so they're represented as a VA, let's say. In order to say the positive, you're going to have a positive right on top of, on the head of the phasor, let's say. VA positive. Okay, VB positive, VC positive. So again, 3 sets of the sequence components. So this is the positive sequence component. This was the 0 sequence components. The last one is the negative sequence component. So negative sequence component, the first thing is has the same amplitude. So the phasors are of the same length. Then the phase displacement between them is 120 degree. degrees. And the last one is, so again, if you rotate it in the center in counterclockwise direction, you're gonna see A is followed by C, C is followed by B. And again, you can start anywhere. So you can start at C, so C is followed by B, B is followed by A. Or you can start at B, so B is followed by A is followed by C. Okay. So that's the negative phase sequence. Okay, so negative sequence component. Okay, so 3 sets. So we're gonna convert one unbalanced 3-phase system into 3 sets of sequence components: 0 sequence, positive sequence, and negative sequence components. Okay, so now what they are. So we realize from here, so that's again the 0 sequence component, that's the negative sequence component, that's the positive sequence component. So right here, you draw it, let's say from here, right? In the same, of the same length and in the same direction. So this is parallel. Okay, then you're gonna add the positive sequence. So this is parallel. Then from the tip of that, you're going to add negative sequence. Okay, you're going to add negative sequence. And where's the, so this is going to be in parallel again. And what you realize for phase A, the sum of these 3, the phasor sum, gives you the phase voltage VA. Okay, so the VA phase starts from here and goes until the tip of the last phasor, which is VA negative. So that is what we're saying. We're superimposing. So first step we will do, we will divide the unbalanced 3-phase system into 3 sets of balanced. So these 3 sets are balanced, balanced, balanced. Right? 3 sets of balanced systems. And then we will analyze them. So let's say we calculate VA 0, we calculate VA negative, we calculate VA positive. Then we using superposition principle, we add them together in order to find VA. Okay, and so on. So similarly, so here is VB. So let's say this is parallel to, where is VB 0? There. Okay, and then VB positive. This is parallel to, so starting from there and parallel. The last one is in here, so starting from the tip of the VB positive, these are parallel again, and starting from the starting point goes till the tip of the VB negative, gives you VB. Last one for phase C, so VC 0 parallel, VC positive, again starting from the tip of the VC0 parallel, and the last one is VC negative. So starting from the tip of the VC positive, perpendicular down, VC negative. So that's where it's ending. So starting point, the end point, and this gives you the voltage for the phase C. Okay, so solution to unbalanced systems, again, these symmetrical components. So what we realize from these diagrams, these three diagrams, that we can write VA equals to VA0 plus VA positive plus VA negative. What else we realize? We can write VB as VB0 plus VB positive plus VC negative. And what else? Sorry, VB negative. Similarly, VC equals to VC0 plus VC positive plus VC negative. Now, what else? This is fine. This is what we're going to keep the way it is. We also know that VA0 is parallel to VB0 is parallel to VC0. So, and they're same in amplitude as well. So VA0 equals to VB0 equals to VC0. Okay, so that means in place of VB0 you can have VA0. In place of VC0 you can have VA0 as well, right? What else? So where is VA positive? VA positive is here. VA positive is here. And where is VB positive? VB positive is here. Now, what is the phase relationship between VA positive and VB positive? So, not the amplitude. Amplitude is exactly same. What is the phase relationship? If you see VA0, VA positive, you can write it as any amplitude. Let's say I'm going to say it has an amplitude of VA positive and an angle 0 degrees. Now I'm going to write VB positive. I'm going to say it has the amplitude, which is same as VA positive. So I'm going to write that as it is. And it has an angle of, what angle? What angle it has? Negative 120. Negative 120 degrees, right? Now, I can also write it as VA positive, let's say. So here is the angle positive 240. So I can write it as an angle of 240 degrees as well. Okay. Now I define something. Define what? I define an operator A which has an amplitude of 1 and has an angle of 120 degrees, right? Now let's say here is the operator A, which is 1 to an angle of 120 degrees. A square. A square is A multiplied by A, right guys? So that means 1 to an angle 120 multiplied by 1 to an angle of 120. All right? That means I'm going to say equals to. So how do you multiply the two polar numbers? You multiply the amplitudes, which is 1 times 1, and you sum up the angles, which is 120 plus 120. So 1 times 1 is 1 to an angle 240. So that means A square is 1 to an angle of 240. Now I'll say, let me say that here, I'm going to do it as VA positive multiplied by 1 multiplied by to an angle of 240. Okay, so this whole thing is your operator A square. So that means you can do it here saying VB positive equals to operator A square multiplied by VA positive. Make sense? So that means, let's do it with this. So VB positive can be replaced by A square times VA positive. Make sense, guys? Okay. Now, next factor in that equation. So the first equation is very, very clear. VA equals to VA0 plus VA positive plus VA negative. Now we're working on the second equation, how we can express the VB in terms of the sequence components of phase A only. Okay, so that we don't need to work with all of them. Okay. So Let's all right, so let's clear some parts of it so that okay, so we're saying VB positive is replaced by A square VA positive, and now we're working on, let's use red and VB negative, how we can express it in terms of VA negative. Now, here is VB negative and here is VA negative, okay? VA negative is, let's say, has an amplitude of VA negative and has an angle of 0 degrees, of course. Now, VB negative, let's say, is has the, of course, the same amplitude, so these two are of the same length. So that's why I can say it also has an amplitude of VA negative. But it is an angle of positive 120 degrees, right? How positive 120? So there is positive 120. Now this is a little bit easy. So we can say VA negative multiplied by 1 multiplied by, obviously, to an angle of 120 degrees. And we already said this is simply A. So we can say VB negative equals to A VA negative. Make sense? And that is what we said actually. VB negative is replaced by A VA negative. Okay, let's move towards VC now. So VC is VC 0, which is same as VA 0. And let's see what is VC positive. So for VC positive, here is VC positive and here is VA positive, same amplitude. So VC positive equals to, let's say, has the amplitude VA positive and it has an angle of positive 120. So that's VA positive times 1 to an angle 120. And this whole thing is A. So A times VA positive. And there it is. So VC positive is A VA positive. Okay. And now the last one is VC negative, which is in here, in terms of VA negative. So VC negative, let's say, has the amplitude VA negative. So this is just the amplitude, okay? That means these phasors are of the same length. To an angle of, I'm going to write this time positive 240, straight. So positive 240, okay? And as I explained previously here, so VA negative times 1 to an angle 240, okay? And as I explained previously, I said this is your A square. A square times VA negative, okay? So that is A square VA negative is VC negative. So here we said operator A is 1 to an angle of 120 degrees. So you can keep writing those angles, that's fine, but we are just simplifying, saying we're going to have one amplitude, angle 120, represented by an operator A. Okay, so here we are writing the phase voltages in terms of the symmetrical. So that's the final equations. That's VA, phase voltage in terms of symmetrical components. VB, phase voltage in terms of symmetrical components. VC, phase voltage in terms of symmetrical components. We can write it in matrix form. Okay, so we can write it in matrix form. How? So this is going to be your vector, which is right in here. And then the other vector is going to be VA0, VA positive, VA negative in here. So the first equation is 1 times VA0, 1 times VA positive, 1 times VA negative. So 1, 1, 1. 1 times VA positive, 0. 1 times VA positive, 1 times VA negative. Of course, you have to sum up the values too. That equals to phase voltage A. Now VB equals to 1 times VA0, so 1. A square times VA positive, A square times VA positive, A times VA negative. And the last one VC, so VC 1 times VA positive, A times, 1 times VA 0, A times VA positive, A square times VA negative. So this is called phase voltage vector. This is called voltage vector of symmetrical components. And this matrix, 3 by 3 matrix in the middle, in here, that is called transform matrix. What it does is, it transforms the symmetrical component quantities into phase quantities. So you might realize what we have done. We have divided an unbalanced three-phase system into a set of symmetrical component systems. Then we have solved for the symmetrical component values. Then we are using transform matrix, which transforms the symmetrical components into phase voltage values, which is required. Yeah. Okay, so here what we have done is, now the other idea is that we might need to transform the phase voltage vector into the symmetrical components vector. So then we're saying in this case, what we need to do is we have to have the inverse of that. So earlier we had like this. I believe this is how it was. Nope. Sorry, this was A square. And here was VA 0, VA positive, VA negative. Let me make sure that it's okay. So earlier it was like this. Now we're saying we want them and we know this. Then what we have to do is we have to take inverse of this matrix. So the inverse of the transformation matrix, transform matrix. So here we are not showing the inverse, but we are just assuming that this is the inverse of the transform matrix. Okay, so we're not going through that derivation, but this is the matrix 1/3, and you also see, please pay attention, it is A square. It is A square, it is A. So this matrix transforms the phase quantities into symmetrical component quantities. All right, so see what we have in here. This is just an example for us to practice. Although we're going to practice more examples in the tutorial, maybe we will, in fact, give me a second. Now this is an example showing us very good concept. So here the three-phase system is given, okay? And if you pay attention to the three-phase system, what do we observe in here? The three phases have same amplitude, and the phase displacement is 120 degrees. So this is a balanced system actually. Balanced system, okay? Balanced system. Now let's try to see if we try to use the method of sequence components, what happens in there. And this will also tell you something which we always use in your 6th semester course, the power system protection course. So we say it many times. So we are given the phase voltages, these phase voltages, we use the, and you know what I think here? Yeah. So we're going to use the inverse of the transform matrix, which is 1/3, 1, 1, 1, 1A square, 1A square A, which is correct, to have the value of the symmetrical components, okay? So we're going to say VA 0 equals to 1/3 VA plus VB plus VC. So VA plus VB plus VC, okay? And you are aware, if you add 277, angle 0, same amplitude, angle negative 120, same angle, angle positive 120. So you can use your calculators to do the addition in the polar form, and you're going to get a result of 0 degrees. Now you do VA positive. What is the VA positive? 1/3. 1 times VA. So that means this is VA. And then you have A times VB. So this has to be A times VB. What we mean by that? So A times VB mean A by itself, VB, sorry, 1 to an angle 120. VB to us is 277 to an angle negative 120, right? Okay, so you multiply 1 with 277 for the amplitude. You sum up the angles, algebraic sum. So one is positive 120, other is negative 120. So this gives you 277 to an angle of 0 degrees, which is right in here. Next you have is A square times VC. So A square times VC will be, let's say we do it here. A square is 1 to an angle 240. VC is 277 to an angle positive 120. So 1 times 277 to an angle 240 plus 120. So that gives you 1 times 277 is 277. 240 plus 120 gives you 360 degrees. Make sense, guys? So that is A square VC, and exact same as this. Okay, so the last line is VA negative. Okay. So for getting VA negative, first term is 1 times VA, which is simply VA. Second term is A square VB. Okay, so A square VB, which is 1 to an angle 240. VB is 277 to an angle negative 120, which is 1 times 277 angle 240 minus 120, which is 277 angle positive 120. So A square VB. There you go. Right, guys? A square VB, 277 to an angle positive 120. The last term you have is A times VC. So A times VC. A times VC, not square. Okay, so A times VC is 1 to an angle 120 is the operator. VC is 277 positive 120 degrees. So which is 277, 120 plus 120. 277 to an angle 240 degrees. And let's see if that is the case. The answer is yes. So again, if you use your calculator here, the result comes as 277 angle 0 degrees. Here the result comes as 0. So what do we observe? In case of a balanced system, there is no zero sequence, there is no negative sequence, there is only positive sequence, voltages or current present. So the balanced three-phase system with positive phase sequence, because you saw that here you also have B is following A, C is following B, so it's a A, B, C phase sequence too, positive phase sequence. So balanced three-phase system with a positive phase sequence have no zero sequence components, have no negative sequence components, has only positive sequence component, because that is what it is. So that's the case of the balanced system.